the principle of relativity. And that would be Galileo. Surprisingly enough, this was one of the first real scientific discoveries that came out in physics. Back when Galileo was coming up with the scientific method itself, he came up with the following idea that motion only really means anything relative to something else. Let me work on the focus here for a second. Now, I guess maybe we can understand where this came from, that if you're measuring motion, how fast are you going? You're measuring relative to something else, but usually that's the ground. And Galileo's big insight was, well, if you're moving, you can just pretend the ground is moving. It's symmetric. It can work both ways. Now, I need a little disclaimer here. What I'm about to show you is state-of-the-art in physics, but I realize in a room full of art professors and art students, this may seem a bit baffling and amusing, if not outright disturbing. But I understand from talking to James that you have this thing called perspective now. I need to talk to you about that in detail. And, okay. So the idea here is that you have somebody on a train moving, say, at 60 miles an hour, while two people are throwing a baseball between them, say, moving at 20 miles an hour, according to the people on the ground throwing the baseball. But from somebody on the train's perspective, you could equally well imagine that the people are moving, say, at 60 miles an hour, and the baseball is moving 80 miles an hour. And the question is, which of these viewpoints is correct? Is one of them more correct than another? Is somebody confused about what's happening? But the whole principle of relativity is that not only are they both correct, but they both predict the same results. They both predict, both of these perspectives predict that the ball arrives at the person at the same time. You get the same physics regardless of which perspective you're in. So whether you're moving in the train and consider that to be still and everything's moving, or whether you're standing on the ground and you consider the baseball and the train moving, it doesn't matter. Furthermore, and maybe this goes a little beyond what Galileo came up with, but all the physics laws that you see in one perspective are the same in another perspective, so long as those two perspectives are moving relative to each other at a constant velocity. The constant velocity just means you're not speeding up or slowing down. There's no acceleration. And we'll come back to acceleration at the end. But the general idea is that these laws of mechanics of throwing baseballs work regardless of which reference frame you're in. And that is the principle of relativity. And it really does predate all the stuff that Einstein did. It was around. People knew about this. This didn't really cause any trouble, though, until about 1860s, when Maxwell came up with his Maxwell's equations. Yes, we're going to have one set of equations here. They're sort of scary looking, but there they are. We don't need to understand them. They are Maxwell's equations of light in a vacuum. And basically, they're talking about the electric field and the magnetic field. And there's this c term in it. There's 1 over c on the right side there. That is the speed of light. Now, when Maxwell came up with these equations, there was no c in it. There were these other constants that were measured in the laboratory doing electromagnetic experiments with electricity and all that. But they were equivalent to c. When he got these equations, he realized that this is basically the speed of light. And he deduced that from his equations that what light is, it's a wave of electric field and magnetic field. It's an electromagnetic wave that's moving through empty space. And from his equations, from just the raw equations, he came up with the speed that these waves would move through empty space. And the speed was c. The speed was the speed of light. And this was huge, huge news in the world of physics, because now they knew what light was. Nobody knew what light was until now. And now that the equations for electricity and magnetism pops out a wave moving at the speed of light through empty space, everything sort of made sense, with one little subtle issue. Relative to what? Everyone knew that motion was all measured relative to something, but now here are these equations popping out of speed that don't seem to be relative to anything. It's just this magical, mysterious speed that comes out of these equations, based on things you can measure in the laboratory, and it has to be relative to something because the principle of relativity says all motion is measured relative to something. So this seemed to contradict the principle of relativity. So the solution that Maxwell and pretty much all the others thought at the time was that the speed of light is relative to some ether, some substance nobody knew what it was, it permeated the universe, and that there was the medium that light would travel through. Because if light is a wave, all the other wave analogies had medium, like a water wave will travel through water, and a sound wave will travel through air. Everyone figured, well, a light wave has to travel through some medium. Let's call it the ether. The problem is that all the attempts to find or measure this ether very quickly failed. In the 1880s, there were these seminal experiments to look for the ether, and there's no ether. And this was really fundamental trouble. And so where's this ether? So now we come to Einstein. And Einstein's insight was to imagine that what if light is moving at a velocity c relative to everybody? What if the reason the equations are spitting out this number is that it's sort of a universal number, regardless of how fast you're moving? You would now have light moving at the same speed relative to everybody. Now this would be very weird. I mean, we now get a picture like this, where whether you're in the train or on the ground, that guy shining it, that's a high-tech flashlight or laser, I believe. There's little lights going out. It doesn't matter what your perspective is. From the perspective of the person on the ground, the light is moving at a speed c. And from the perspective of the person on the train, the light is moving at a speed c. Even though they're moving relative to each other, the light apparently is still going the same speed relative to both of them. And pretty much anyone who had thought of this before Einstein probably quickly realized this is impossible. There's no way this can happen, because if you're moving relative to light, it has to be going faster or slower, depending on which way you're going. But Einstein stuck with it, and not only stuck with this, but he said, well, the principle of relativity, which he stuck with, he said that both views, whether you're on the ground or on the train, are equally valid and better have the same physics explaining it. And reconciling a constant light speed with the principle of relativity sort of inexorably leads to the special theory of relativity. Those are the only postulates you need to come up with a special theory of relativity. With those two postulates, unfortunately, or fortunately, depending on how you look at it, you have to start mucking with space and time. Because the only way that you could make sense of those two pictures is to actually have space and time be relative to how fast you're moving. When you're measuring a velocity, you're measuring something at one space at one time and another space at another time. And so in order to keep c constant for both observers, you have to start either changing space or changing time in a way that will make this happen. So that's the foundation of the special theory of relativity. Those two elements. Okay. So let's look at a consequence of special relativity. We're only going to look at one or two here. But let's imagine that we have a clock, but instead of an ordinary clock like we're used to, let's make a clock out of two mirrors and a pulse of light. So those are two mirrors, and that little red dot is a pulse of light. And it is moving back and forth, bouncing between the mirrors. And you could build a clock like this if you had a small enough pulse of light. And you could have the clock tick every time the light hit the bottom mirror, say. So that would be one tick of the clock. And it would tick at a regular rate, and you'd have yourself a clock. Now, imagine viewing that clock from a moving train. And as you view it from the moving train, as the light is bouncing up and down, you're still, right? You're in the train. You're imagining the mirrors are going by you. So as the mirror goes by you, it moves first. These are three different times. There's one time you have these mirrors, the light's down here, and then the light has to somehow get up here for the next mirror because it hits the center of the mirror again, and it's going to hit the center of the mirror on the way back down. And that means from your perspective, the light is traveling at an angle. Right? It's the only way it can get from this point to that point to that point. As the mirrors are moving, you see the light moving at an angle. So, I already just said that. No, here's the rub here. But because the light is still moving at the speed of light, at c, it's now going a lot further. So it's going to take longer to get to tick, right? It's going to take longer to go up to the top mirror and down to the bottom mirror, just because it has further to go. And it can't speed up. It can't go at a different speed. Light always moves at the same speed. And the only conclusion you draw from this is that the clock appears to be ticking slower. Every time the light hits the bottom mirror, it ticks once, remember. So now we have fewer ticks at the same rate, and the clock has appeared to slow down. And Einstein went on to generalize, no matter how you build the clock, it's going to slow down. A moving clock is going to seem to slow down. So time itself, how we perceive the rate of time, is depending on relative velocity. So let's compare two clocks. I didn't tell you the names of these figures, but their names are Ann and Bob. And each of them have a clock, clock A and clock B. And suppose Ann is moving with a velocity v relative to Bob. Now, of course, you could equally well think of it as Ann being still and Bob moving, as we've already discussed. But let's look at it from Ann's perspective, or from Bob's perspective first. From Bob's perspective, he sees that Ann's clock is going slower than his own. Because it's moving relative to him, so it seems to slow down, just like we discussed on that last slide. But the other perspective means that from Ann's perspective, Bob is moving. And so she thinks that Bob's clock is moving slow. So they both think the other person's clock is moving slow, which is pretty weird, because you'd think that you could make a contradiction. Eventually, if I had a clock and I said, your clock's running slower, you say, no, my clock's running slower, well, we just keep comparing it and seeing who is really right. And the question is, can they both be right? And the answer is yes, actually, because they don't even agree about what now is. We think we know what now is. I mean, if everyone in here snaps their fingers at the same time on the count of three here, 1, 2, 3. We all heard that at the same time. We said, okay, that's now. Everyone did it at the same time. But somebody flying near the speed of light through the room while that happened would not have experienced what we just experienced. They would see people over, which way is it? People over here snap first, and they would see a sort of a snap ripple run across the audience. Somebody running the other way would see the snap ripple going the other way. The definition of what now is now up for debate, depending on how you're moving. And because of that, the only time that they can be sure to agree on when now is when they pass each other. But if they don't accelerate, that only happens once, right? They just pass each other, they check their clocks at one time, and then they can't agree on when now is after that. In order for them to check it twice, one of them would have to turn around and accelerate and come back the other way. And then it gets more complicated. But because, as long as they don't accelerate, they both can be right, actually. They both can say the other person's clock is going slower, and everything can be consistent. They only check their clock at one point, so they set it at noon when they pass each other, but they have no way to tell after that whose clock really is running slow. In fact, they're both running slower relative to each other. And so, let's end with what happens if somebody does turn around. And once you start accelerating, now we're getting more complicated. Now we're getting into general relativity. And so this is a space-time diagram, we're getting very fancy now, where time is running down here. So Ann at one time is at the beginning, and then later she's still in the same place. Sideways is space. So Bob is moving at some velocity here. He's moving in time and space. And then at some point, he changes his velocity or accelerates and heads back the other way. So now they can compare their clock at two different times. But in this case, because there's been acceleration, the symmetry gets broken. So they now agree when he gets back that Ann has aged more than Bob. And if Bob is traveling fast enough off in a spacecraft and turns around and comes back, he might see hundreds of years go by on the Earth and only age a short amount of time if you're traveling really fast. None of these effects happen, of course, unless you're traveling near the speed of light. So we don't see this in a regular everyday experience, but we do see it in the physics lab when particles are moving at the speed of light and other things like that. I guess I'll end with Einstein's key insight to generalize special relativity, which is his really big breakthrough for general relativity, or GR. And his key insight was that acceleration due to a velocity change, like we just saw with Bob, has to be indistinguishable from acceleration due to gravity. This is called the equivalence principle, and it's basically what he built general relativity around. This was the key postulate, and it is a beautiful theory in the sense that it starts from a very few postulates, but it's very ugly in the sense that the math gets really nasty. But he was able to tie in gravity to this stretching of space-time and basically reinterpret gravity as a deformation of space and time. And that was really his greatest achievement from a physics perspective. But what started it all was the theory of special relativity, which you'll be hearing more about very shortly.